Welcome back. We are trying to find the solutions of ordinary differential equations. So, now onwards we will move on to partial differential equations. So, in this we only study a linear partial differential equation of second order. Only second order linear partial differential equations we take and we try to give you, we classify them. So, we will talk about what is the classification. We will classify these equations and put it into one of these forms, one of the three forms. So, we will give you each of these form will give you so well known equation. Those equations with the initial and boundary data we will try to solve them in the next few lectures. Okay. So, what is a partial? So, what is a second order linear partial differential equation? So, first of all let me write what is the linear. So, linear means so you should not have, if the dependent variable u should not have, so u square, only u and only u should be there. Okay. So, that is crudely what is a linear. Otherwise you have L u equal to 0 if this is your equation. L is the differential operator that is involving derivatives or partial derivatives or ordinary derivatives. Okay. So, once you involve mathematically, you take a combination C1 u1 plus u2, u1 u2 are two solutions of this, then you apply this, then this will come out as L u1 C into L u1 plus L u2. So, if it comes like this, then you say that this L is the linear differential operator. Okay. So, we will see what is the second order linear PDEs. So, this is actually PDEs. Is general, is in the general form as given by this. You take, so a some function of x y, all these a b c d what I write as a coefficients of this partial derivatives. So, it is a second order. So, you have two x derivatives which I denote like this as a subscript. U is a dependent variable u of x y is a 2, if you have two variables. So, two independent variables x y and u is the dependent variable. So, that is why it is a partial differential equation, a second order, because you have two derivatives, two partial derivatives and the coefficient is functions of x y. So, a is this plus, so I do not write now on what's a of x y. So, this is simply a b u x y plus c u y y plus d u x e u y plus f u equal to, if it is a non-homogeneous equation, so you will have some function of x y. So, this is what it is, you have, this is a linear function, because you try to put you replace u with this, it will always come out. Okay. This differential operator left hand side you can always write in this form. Okay. So, that is why it is this is a linear, you can see that there is no u square or only u terms. Okay. The derivatives of u and u only. Okay. And the coefficient should not have any functions of u. So, all these a b c d f, okay, a b c, where a b c d e f g are functions of x and y. Then you say that this is the linear partial differential equation. So, how do we solve this if it is general form? Okay, it is not easy. So, we cannot solve in general any partial differential if you are given in a general form. So, what we do is, first of all, to study this equation we will try to classify them. How do we classify them? So, the motivation comes from the quadratic equations. So, quadratic equations, if you consider quadratic equation, okay. So, what is the quadratic equation? A x square plus b x y plus c x square, let us say, equal to 0. So, if you have this quadratic equation, you have quadratic equation like this is y square, c y square. Quadratic equation is this. How do you classify? As a conic sections. Okay, this is depending on this discriminant b square minus 4ac. If it is positive, you call this hyperbolic. Hyperbola. Okay, if this is if any quadratic equation, when you have this discriminant is positive, it is actually hyperbola. If this is 0, it is called parabola. It is parabola. Okay, that is how you classify it. And b square minus 4ac is less than 0. This is ellipse, right? This is how you classified this quadratic equations. In the same way, we say you can see that this equation, instead of x square you have two x derivatives. If you have xy, you have a mixed derivative with xy, two derivatives. It is a quadratic, and I have a second order here, and I have the coefficients, they are functions of xy, these are here constants, and this is of this form. So, analogically, even for the PDE, so we will classify. So, we will classify the equation. Okay, classify the PDE in the similar lines as if b square minus 4ac, the discriminant, we call this delta. Okay, if the delta is this, if this is positive, you call this, the equation is then hyperbolic equation. If the discriminant is 0, parabolic equation. And if the discriminant is negative, it is called elliptic equation. Okay, much similar to how you classify the quadratic equation, because each equation when it is positive, its characteristics are different. Okay, so in each of these cases, each equation is as having different characteristics. So, in the same way, so we also can expect. So, that is why we coined these names, same names, hyperbolic equation if the discriminant is positive, otherwise parabolic equation, elliptic equation, you classify them. You can expect each of these cases a different each different equation. So, each equation here will be different, having different characteristics. Okay. So, that is what we see, how to get them. So, we classify such an equation. So, we try to classify this equation, second order general equation, into one of these three types. That is, putting into one of these forms is called, if it is a hyperbolic form, if it is a hyperbolic equation, if this discriminant is 0, if it is positive, it is hyperbolic equation. So, in that case, if we try to look for new variables, okay, so you are having independent variables x, y now. So, you try to look for new independent variables, some xi and eta, and you do the change of variables, and the equation becomes, in this case, is similar to a wave equation. Okay, you get the wave equation type. Wave equation, second order terms looks like wave equation. So, that is what is a hyperbolic equation. The typical equation you will get here, you will get heat equation. Okay. So, if your discriminant is 0 and you try to change this equation into this form, parabolic, if you work out, you reduce, you look for new variables, some xi and eta, in those new variables you get heat equation. In this case, in terms of these new variables, you get Laplace equation. Okay. This is how you classify. When you classify, these are the types you get. Typical equations are wave, heat and Laplace equations. So, we will try to see how do we classify these equations. So, let us take this general form. So, what you need is you are looking for basically change of variables. So, x, y 2. So, you want to take these x, y variables. So, let me write x, y as a vector in this way. So, x, y variables to new variables xi and eta. Okay. This is the transformation, change of variables transformation xi and eta. So, when you go from xy to xy, xi and eta are functions of xy, eta is equal to eta of xy. So, this is how you look for new variables. So, when you go to when you are changing these new variables x, y to xi and eta, because x and y are linearly they are independent variables. Okay, they are independent variables and they are actually. So, in the same way, so when you go to the new variables xi and eta also should be linear independent variables, should be independent variables. Okay, the transformation from, so x and y is actually from R2 to, so xi and eta. So, you have a transformation, the transformation is actually, if you call, a vector valued function, okay, from R2 to R2. So, you are in the plane xy to a new plane. So, the xi and eta, something like you take the Cartesian coordinates, you convert this into curvilinear coordinates, maybe something like this. Okay, this is your xi and eta, something like this. Okay. So, that is how you are trying to see what is the, this is your x y, if x equal to 0 is y axis or y equal to 0 is x axis, your lines are, if you fix y equal to constant, some constant is this line, x equal to constant is this line. Okay. In the same way, so xi equal to constant is this line, okay, eta is constant is this line. So, this is how you try to see when you, after the transformation, these lines become, these parallel lines becomes the parallel curves. Okay. So, that is how you look for the transformation. So, I can always find some transformation to take from this to some other figure, okay, some other thing. If you really want this, you should be able to come back. Okay. And you want, when you transform, you should be able to come back whenever you want to. Okay. So, you want to have a transformation, you should have inverse transformation. So, to get this inverse transformation, I should have f dash, this f inverse should exist, okay, at least locally, okay, should exist, then I do not have issue. So, I can always come back. That is, what is the meaning of this? I have xi and eta in terms of x y. When f inverse exists, I should be able to write x in terms of xi and eta. I should be able to get x and y in terms of xi and eta. That is the meaning. Okay. That is, so I should be able to get this x in terms of xi and eta, y also in terms of xi and eta. So, what is the best way to do this? So, if you are given this one f from xi and eta are the functions. Okay. So, actually what you have is f bar of x y equal to is actually, this is a vector is x y. Okay, this is the vector, f bar of x y is xi of x y and eta of x y. This is how this transformation takes. Now, this is a vector and this is also a vector right there. So, when you apply, so function of this vector is a vector, this is how we have. So, I have xi and eta in terms of x y. So, when can I say that f inverse actually exists? I can go back, I can actually write in terms of x y in terms of, I can have a inverse, okay. I can write x y, I can have f inverse exists. So, this is through a derivative of a function. So, I digress here. So, if suppose you have a function f which is from a real valued function, this is not a vector valued, this is only from real valued function and it one variable, okay. Just take one variable. What is its derivative? Suppose it is a differentiable function, the derivative of x is actually df by dx, right. Df by dx is this at x, okay, is equal to, this is this value at x equal to x naught. If you want a derivative at x naught is in real, this is what it is, right. What if you have Suppose this okay, so let us suppose this derivative is non-zero. What is this one? What is actually this f? F is a curve in this line. Okay. If the derivative, if you always, so what is the derivative is non-zero means it is not parallel to x axis. The tangent at any point, a tangent is not parallel to x axis. If it is parallel to x axis, then it is 0. Okay. So, if it is not parallel to x axis, I can always, so you look at this point, I have, you look at the neighborhood. In this neighborhood you find all the tangents. Okay. If none of these tangents say, let us say at this point, okay, at this point you look at the tangent in the neighborhood of this all the points here, you look at the, for the curve you look at the tangents. The tangents are not parallel to x axis, that is the meaning of x naught. Now if f is continuous and f is differentiable and it is also continuous, so the tangents are moving continuously along the curve. Suppose if you assume that is what it is, if all the tangents to the curve are continuously moving, okay, that means derivative is continuous, and we know that it is non-zero at one point by the property of a continuous function. It should be in the neighborhood of this, at all in the neighborhood, that means up to here, you take the tangents in between for the curve, they are all non-zero. Okay. So you have f dash of x is actually non-zero. If it is at one point it is non-zero, which is non-zero for every x in the neighborhood of x naught. Okay. Say let us say x naught minus delta, x naught plus delta. So some delta neighborhood you have this, this is your x naught plus delta, x naught minus delta. So within this interval, if you consider, so the derivative is also non-zero. So you see that at one point if it is non-zero, and in the neighborhood it is non-zero everywhere. So once this derivative is non-zero, you can see that these tangents are not parallel to x axis. That means you can actually see that the inverse actually exists, inverse function actually exists. Okay. Only problem is if the derivative is 0, it is a parallel. Here at this point it is parallel to x axis, you cannot have inverse, because at this point for the y axis, if you look at the y axis, at this point I have in the neighborhood, any point you pick up, I have 2 values. Okay. And the close you have 2 values, it is not defined. Okay. But if the, because the derivative is 0, that means the tangent is parallel to x axis. If it is not, if the derivative is non-zero or the tangent is not parallel to x axis, you can see that you can have an inverse. Okay. You can define in the neighborhood of this point, if this is x naught, this is my fx naught, that is as your y naught. So there is some epsilon neighborhood. So some neighborhood I can always find an inverse. Okay. Within this interval I can define, I can see that I can define this function, okay, which takes, I can have an inverse here, you can see this. Okay. So what is that we are trying to say is, if the derivative is non-zero, you have inverse exists. Okay. For a continuously differentiable functions. Same thing, now you consider from f is from R2 to R2, R2 to R, multivariable function. So that means f is a function of x y. Now what is its derivative? df. So if you call this vector, you call this df by d x bar. X bar is a vector in R2, plane vector. Okay. If this is at x naught is also vector, should be equal to, this is dou, what is this one? Is actually what is the derivative here? So you have you have 2 variables, which is, if you from the calculus you can see that dou f by dou x and dou f by dou y, that is what is your derivative. Okay. 2 partial derivatives. So this is, as you can see this as a matrix, this is 1 and 2. So if your function is from R2 to R1 and you see this range is R range is a Euclidean space with 1 this 2 here. So, 1 by 2 matrix. So, you can see that the derivative is actually at 1 by 2 at x equal to x naught. So, you consider at x bar equal to x naught vector. So, you see that derivative is actually it is a operator, linear operator is you do not know what is linear operator, but this is, you can think of as a matrix. It is a matrix 1 by 2 matrix, range whatever r power, that is 1 by 2, that is what is, this is how you represent this derivative. So, what is the meaning of this derivative is non-zero? That means this, what do you mean by this is non-zero? This means you have to consider df by dx bar, this modulus, okay, this quantity you have to take non-zero, okay. Then you may have some inversion. You see inversion here it is not possible because this is from R2 to R1. So, inverse obviously is not, you cannot have, right, R1 to R2 you may have. So, let us not this may be a little cumbersome to talk about the inverse. Now, so in this way if at all you consider that the inversion I mean the derivative is non-zero, this is how you have to take. You simply I want to tell you that this norm, or you say this is a distance, is a vector. So, the distance, okay, that is a modulus value of the vector should be non-zero, that is the meaning of non-zero derivative. Now, what we have is a function from R2 to R2, a function from, this is a vector valued function now, that is why I put a bar R2 to R2, okay. So, what is its derivative? df bar by dx bar at x naught, this is at the, this is actually equal to, now what is my f bar? F bar is actually f bar of x bar equal to, let us say f1 of x bar, this is like a earlier function this, and similarly f2 of x bar. So, you have two components, each of this is like earlier type. Now, what is this one? So, this is a vector. So, you should write this is a vector. So, you should write like f1 of x bar, f2 of x bar, okay. So, it is a vector in R2, this is how it is. So, if you actually see, now I know that what is the derivative of this one, this you know from here, this is the derivative. So, you write it. So, dou f1 by dou x and dou f1 by dou y, okay, that is 1. And similarly for f2 you write dou f2 by dou x, dou f2 by dou y. So, what you have, this derivative is actually earlier is 1 by 2 matrix, now you have 2 by 2 matrix, 2 by 2 matrix. So, the derivative is actually 2 by 2 matrix. What do you mean by the derivative? So, the derivative is non-zero here means this distance, the modulus, what is the modulus here? You can take a determinant, okay. This is a determinant of this matrix, okay. This is non-zero, this is non-zero means a determinant of df bar by dx bar, which is f dou f1 by dou x, dou f1 by dou y, dou f2 by dou x, dou f2 by dou y. This has to be non-zero, that you can calculate, right. So, if the determinant, if it is from R2 to R2 function, a derivative is actually as a matrix 2 by 2 matrix, and it is non-zero means the determinant has to be non-zero. That means then you, as like analogous to this curve, when you have the derivative is non-zero, the tangent is not parallel to x axis, you can have the, you can see that there is an inverse in this case also, in these three cases also. In this case from f is from R2 to R2, and the derivative which is this determinant, this is called a Jacobian of the matrix, okay. This is Jacobian, is when the Jacobian is non-zero, we write J, this Jacobian is non-zero, that means you can have an inverse f inverse, okay. So, this exists, so I can write now what is my f1 is my xi, f2 is my eta. So, what should I say, if I have this exists, okay, f inverse exists, f bar inverse exists if Jacobian, which is a definition is a determinant of xi x xi y eta x eta y, which is non-zero. If this Jacobian is non-zero, that is determinant of this matrix, then you have in this inverse exists. So, you should always look for your xi and eta functions in such a way that this Jacobian is non-zero. I can anytime I can, if I want, I can go back to a new old variables x and y. Okay, you do not lose anything. So, one to one correspondence between x y variables and xi and eta variables. This is what you should know before you transform this equation into a new variables xi and eta. Now, having observed this thing, what we do is we are looking for a new variable xi and eta. So, we are trying to change a transformation xi with this xy to xi xy and eta xy. So, this is a change of variables. So, we want to replace all the derivatives of x with the derivatives of xi and eta. So, to do this, so we have to replace a derivative ux. What is ux? I want u is basically u is a function of xy first of all. U is a dependent variable which is earlier function of xy. Now, if the Jacobian is non-zero, okay, eta is xi of xy, eta is eta of xy, okay, and the Jacobian is non-zero, that implies I can write x in terms of x of xi eta, y in terms of y of xi eta. So, x I can replace in terms of xi eta, y in terms of xi eta. So, finally becomes u is a function of xi eta, but xi is function of xy, eta of xy. Okay. You can simply say that this is xi and eta. So, what you have is ux dou u by dou x is actually equal to dou u by this variable dou xi and dou xi by dou x plus dou u by dou eta into dou eta by dou x. That is what is my dou u by dou x. You try to see this one, this you can replace with dou xi by dou x, just rewrite, okay, this you put it front and this you write next, dou u by dou xi plus dou eta by dou x, this you write first and this is next, dou u by dou eta. So, if you write this, this is what is your dou u by dou x, and you remove this u, this is just like operator. Okay. If you remove this, what you get is from this you have dou x is in this form. I know what is my xi is a function of xy, I can calculate xi x, I can calculate eta x, okay, eta is a function of xy, I can calculate my eta x. So, that will give my dou x. In the same way, you can similarly, I can get dou u by dou y as dou u by rather dou xi by dou x into dou u by dou xi, dou u by dou xi by dou y plus dou eta by dou y into dou u by dou eta. So, that implies dou y is actually equal to dou xi by dou y into dou xi plus dou eta by dou y into dou eta as an operator. Okay. Now, you take your equation. So, what you have is uxx, what is this one? Dou square u by dou x square, this is dou x into on the dou u by dou x. Okay. This itself is acting on u. So, this is something like this, dou u you apply to u. So, dou x you apply to u. So, but now I replace dou x with what I have. Okay. What I have is, so I can have xi x dou xi plus eta x dou eta, that is for dou x. You repeat one more, xi x dou xi plus eta x dou eta acting on u. So, if you are acting on u, first one will give you dou u, simple. Okay. And now you expand it nicely, what you see is if you expand it xi x dou xi of this one. So, that will give you what you get. So, xi x dou xi by xi x. Okay. So, I will write directly, you will see that u x x will be, okay, you can write it. So, dou xi of acting on xi x u xi plus eta x u eta. Okay, this I am writing like this, plus eta x dou eta of xi x eta xi plus eta x u eta. Now, you look at this one, this will be xi x, and what you have, this you are differentiating this first term. So, that will be dou xi of xi x into u xi, okay, plus, now if you differentiate this one. So, you have xi x here, xi x here, xi x square u xi xi. Okay. Similarly, you get xi x dou xi of eta x, okay, into u eta plus xi x eta x into u xi eta. This is what if you expand this one. Okay. Similarly, you do this side, you will get, now this term if you do it, 4 terms you will get. Okay. So, you simply write xi you replace with eta. So, eta x, now look at this one, dou xi dou eta of xi x u xi plus eta x xi x u xi eta, now plus this one. So, eta x dou eta of eta x u eta plus eta x square dou u, so dou eta of u eta. So, that is u eta eta. So, this whole thing you can see this one. So, you look at the second order terms, you write separately. Okay. So, if you write this, what you get is u x square u xi xi plus this one together. So, these are derivatives, you can assume that they are continuous functions, u two mixed derivatives. So, you have a 2 xi x eta x u xi eta, okay, u xi eta, and then plus eta x square u eta eta. Okay, this is what you have, plus some coefficient. What is actually this xi x into, so dou xi of xi x. This you can say xi is a function of x y. So, you can rewrite this, so dou x of xi x into dou x by dou xi. That is what you see. Dou x by dou xi is possible because x I can write in terms of xi y because of inverse, okay, because Jacobian is non-zero. So, that way you can actually have this, you can further simplify these things, but you do not need to worry. So, you have u xi, the coefficient of u xi is this one, that will be some function of x y. Okay. So, you have u xi and you have u eta terms and okay, u xi and u eta terms, those are simply lower order terms, you can say them, they are not really important. Okay. So, u x x finally what you get is this one. So, you can write in terms of xi eta and u eta eta plus lower order terms in terms of u eta. Okay. So, if you do similarly, you can get u y is also, you can get instead of x you replace with y. So, you have xi y square u xi xi 2 xi y eta y u xi eta plus eta y square u eta eta plus lower order terms. Okay. Now, what happens? We also have in the general equation u x x u y y and u x y. So, this also you have to write u x y in the same way. What you do is you just have to do dou x operating on dou y operating on u finally, okay, something like that. If you do, again you will see that by the same calculations, if you collect these higher order terms, second order terms, what you get is u xi xi. So, you get xi x xi y u xi xi. Here you get xi x eta y plus eta x xi y of u xi eta plus eta x eta y u eta eta plus lower order terms. Okay. It is not difficult to see. Okay. So, you could see that after transformation in terms of new variables xi and eta, u x x, u y y and u x y mixed derivative. So, this is your, so I have this one and this one. Okay. Now, a is a function of x y, x I can write in terms of xi and eta. So, all these functions a, b, c, d, e, f, g are now functions of xi and eta. Okay. So, this way now if you substitute, go and substitute into your equation all this, you can also calculate, you know now all these things u x, u y and u. Okay. Now, u is a function of xi and eta, and now you can also have u x, that is simply what you have. So, u x is, what is u x? Directly you have already. So, u x is xi x u xi plus eta x u eta. So, this is what is your u x. Similarly, you can get u y, that is xi y u xi plus eta y u eta. So, you have everything. So, u is a function of now xi and eta. Everything I have, you go and substitute into the general form of the second order linear partial differential equation. If you just substitute there, what you end up is, if you collect the terms of u xi xi. See, when you substitute u xi xi, I have a xi x square and I have here, okay, this is c xi y square and I have here, this is b xi x xi y. Okay. If you collect that, what you end up is equation, the PDE becomes, now you have the coefficient u xi xi, the coefficient is whatever you get. So, that I call it some coefficient. What do you have? A xi x square plus b xi x xi y plus c xi y square. Okay. What you have is simply collect the terms a into this, c into this, b into this, and then you add them up, and d, e, f, okay, like that you add. So, I would collect the terms of higher order, that is u xi xi, now this plus I will write now what I have for a coefficient of u xi eta, that is going to be, you will see that it is going to be 2a xi x eta x plus b times, okay, 2a xi x, that is what you have seen, right. So, you have 2 xi x eta x and here this term with b, this term with c, okay, b times xi x eta y plus eta x beta xi y plus 2c xi y eta y, that is what you have, okay, plus what you have is something similar to u eta eta terms. U eta eta terms are something like this. Again u xi y, sorry, u a, what is the coefficient of u eta eta? U eta eta is again eta x square, again here. So eta eta is this one and this one terms. If you do that, you see that is going to be a eta x, everything in terms of etas. Okay, instead of xi you replace with eta, eta x square plus b eta x eta y plus c eta y square plus some coefficient of u xi, some coefficient of u eta, some coefficient of u equal to some. So what you have, what is the a, b, c, d, e, f, g, g you have written, right. So when you finish, what is your general equation? G. So that may become, you may have some terms that will have g star, okay, whatever is the new term is g star. So this I call this f star, okay, this I call this a, b, c, d, e star, okay, this is my whatever coefficient I call is some d star. These are not real lower order terms, they are not important. What is required is you have a star u xi xi, so a star is this, and b star u xi eta plus c star u eta eta plus lower order terms equal to 0. Lower order term means including the constant, that right hand side non homogeneous term is 0. This is how, this is what you get, okay. So where a star is this, where a star is simply a, this a, b, c, d, a, b, c are known. Now a star is in terms of a, b, c, a xi x square plus b xi x xi y plus c xi y square, b star is this 2a xi x eta x plus b times xi x eta y plus eta x xi y plus 2c xi y eta y, and c star is a eta x square plus b eta x eta y plus c eta y square. So you have reduced given partial differential equation of second order linear partial differential equation, you reduce to you using the change of variables, new variables xi and eta. So with these new variables you can go and come back. So it is basically invertible new variables, okay, invertible new variables. You write your partial, you converted your partial differential equation in terms of these new variables, okay. So instead of x, y independent variables, now you have new independent variables xi and eta. So this is what is the, so the given second order linear partial differential equation becomes this type. This is the now, this has become, this is reduced to in terms of new variables xi and eta, okay. So we will see how to classify this in the next video. So we will look at the discriminant a square b square minus 4ac, depending on the sign of this b square minus 4ac, the discriminant, and we will decide how to how this equation reduces, okay, how it will become, what kind of form it takes, so that your hyperbolic equation means it is in this form. You can reduce, a typical equation will be wave equation. Similarly, heat and Laplace equation you can get based on the type of equation, okay, your given partial differential equation is. That we will see in the next video.